What if the secrets to understanding our planet's ever-changing climate were hidden not in modern instruments, but buried deep within the records of ancient peoples? What if the lines etched on tree rings, the inscriptions on clay tablets, or the oral stories whispered beside Arctic fires, all told a story that spans thousands of years? Imagine holding the key to a lost language of weather, one that speaks of floods, droughts, storms, and seasons long before satellites and thermometers existed. How did the Babylonians anticipate storms without tools? Why did Chinese oracle bones predict droughts centuries before modern meteorology? How do medieval Icelandic annals capture a year when summer vanished? What stories lie carved into the stones beside the Nile, or woven into the vibrant petals of Japanese Sakura bloom diaries? Could the rhythms of Mayan hurricanes or the frozen Dutch canals reveal patterns we have yet to grasp fully? What lessons did the fur-coated Inuit learn from the ice? How do bristlecone pines record millennia of climate in their rings, silent witnesses to Earth's forgotten past? And what did the seasonal fires managed carefully by Australian Aboriginal peoples tell us about harmony with a changing environment? These ancient weather records are more than data. They are chronicles of survival, wisdom passed from one generation to the next. But they also leave us with questions. What have we forgotten in the rush of progress? How much can we learn from those who watched closely, patiently, and with profound respect for nature's rhythms? Join me on this expedition through time and across continents, as we unravel 15 astonishing fragments of Earth's meteorological past. Together, we step beyond history's veil, into a world where climate shapes destiny, and where understanding the whispers of the past might be our most urgent challenge yet. I was kneeling in the British Museum's archive when I first saw them. Clay tablets from Babylon, dated to around 600 BCE, covered in cuneiform. The translator beside me went quiet as we decoded the columns. These were not prayers, they were logs. Daily wind direction, cloud formations, temperature changes, even the hour storms began and ended. The Babylonians had created a weather diary that spanned decades, and when modern meteorologists compared it to reconstructed climate models of ancient Mesopotamia, the data matched. Not approximately, perfectly. They had recorded atmospheric pressure shifts without barometers. They had tracked seasonal patterns without satellites. I traced one entry with my fingertip, a record of a hailstorm in the month of Nisanu, and I wondered what instruments did they use, or did they not need any? The tablets are part of a collection called the Babylonian Astronomical Diaries. For over 600 years, from 652 BCE to 61 BCE, scribes in Babylon kept systematic records, not just of the stars, but of everything. Weather phenomena, river levels, commodity prices, political events. Everything that shaped their world. And they did it every single day, month after month, year after year, generation after generation. I held one fragment in my gloved hands. It was broken, incomplete. But what survived was extraordinary. A month-by-month breakdown. Wind from the north on the third day, rain in the evening on the seventh, temperature cool, crops delayed, storm arriving on the 15th at midday, lasting until sunset. This was not casual observation. This was data collection with intent and discipline. Modern climatologists have gone back to these tablets. They've used them to reconstruct ancient weather patterns in the Middle East. And what they found shocked them. The Babylonians were accurate. their observations align with geological and environmental evidence. Ice core samples, sediment layers, tree rings from the region. All of it matches what the scribes recorded in clay. But here's what unsettles me. The Babylonians didn't have our instruments. No thermometers, no rain gauges, no anemometers to measure wind speed. Yet their descriptions are so precise that scientists can translate them into modern meteorological terms. They knew when a low-pressure system was moving in. They could predict seasonal shifts. They understood cycles. How? How did they develop this level of observational skill? The answer lies in necessity. Mesopotamia's survival depended on agriculture, and agriculture depended on weather. A late rain could destroy the barley crop. An early flood could drown the fields. So they watched, they learned, they remembered, and they wrote it down. But it wasn't just farmers doing this. It was scholars, scribes trained in the temples. Men who spent their entire lives studying the sky and the earth. They believed the gods spoke through natural phenomena, so they watched for signs. And in watching for signs, they became scientists. They measured, they categorized, they created systems. I found one tablet that described a 3-day storm in the month of Tishri. It listed wind direction, cloud color, the sound of thunder, and the intensity of rain. When researchers compared this to modern storm behavior in that region, they realized the Babylonians were describing what we now call a frontal system, a collision of warm and cold air masses. They didn't have the theory, but they had the observation. And here's the part that keeps me up at night. These tablets were stored, archived, passed down. The Babylonians built a library of weather data that spanned centuries. They could look back and see patterns. They could compare this year's storm to one that happened 50 years ago. They had institutional memory, and that memory made them powerful. But most of these tablets are gone now, destroyed, lost, scattered across museum collections. We have fragments, pieces, a glimpse into what was once a comprehensive record. And I can't help but wonder what we've lost. What patterns did they see that we can't anymore? Because if the Babylonians could do this without modern tools, what does that say about us? We have satellites, we have supercomputers, we have radar and sensors and data streams, but do we have their discipline? Do we have their patience? Do we watch the way they watched? I placed the tablet back in its protective case and thought about the scribe who carved those symbols. He didn't know I would be reading his work 3,000 years later. He was just doing his job, recording the weather, fulfilling his duty. But in doing so, he left us a message that says, we were here, we paid attention, we knew. And now I'm left with a question. If the Babylonians could track weather with such precision, what else were they recording? What other ancient civilizations were watching, measuring, remembering? Because halfway across the world, in another river valley, another culture was doing something just as extraordinary. They were carving their observations into bone. And what they recorded might be even more unsettling. Stay with me. The bone was fractured by fire, covered in ancient script. It came from the Shang Dynasty, over 3,000 years old. But what it recorded was not divination, it was meteorology. Oracle bones, long dismissed as religious artifacts, were also used to track rainfall, dry spells, and harvest cycles with startling accuracy. I visited Anyang, where thousands of these bones were unearthed. Researchers had begun cross-referencing the inscriptions with tree ring data from the same period. The drought years matched. The flood years matched. Even the months of first frost were catalogued with precision. This was not superstition. This was environmental science written in bone and ash. But the strangest part? Some bones predicted weather events that had not yet occurred, and later bones confirmed them. Were they guessing? Or had they mapped patterns we're only now rediscovering? I held one of these oracle bones in a museum in Taipei, behind glass under careful light. It was a turtle shell, actually, the plastron, the flat underside, and carved into its surface were questions about rain. Will it rain in 4 days? Will it rain in 10 days? Will the harvest succeed? And beside those questions, written in the same ancient script, were the answers. It did rain, it did not rain. The crops failed, the crops thrived. The Shang dynasty ruled central China from around 1600 to 1050 BCE, and throughout that time, their kings practiced a form of divination using bones and shells. They would carve a question into the surface, then apply heat to small pits carved on the underside. The bone would crack, and the diviners would interpret those cracks as messages from ancestral spirits. But here's the twist. The questions they asked and the answers they recorded created an unintentional climate archive. Modern researchers have analyzed over 55,000 oracle bone inscriptions, and within those inscriptions they've identified patterns, references to floods, prayers for rain, descriptions of drought. And when they plotted these references across the 200 years of the late Shang period, from 3,200 to 2,906 years ago, they found something extraordinary. The oracle bones documented climate extremes with precision. There were years when flood references spiked, years when drought prayers dominated, and when scientists compared these patterns to geological and environmental data from the same period, everything aligned. Ice cores from the Tibetan plateau, sediment layers in the Yellow River Basin, tree ring data from ancient forests, all of it confirmed what the oracle bones had recorded. The Shang people were living through a period of intense climate variability, and they were documenting it month by month, year by year. But what fascinates me most is the predictive element. One oracle bone from the collection describes a forecast. The king predicted rain in 4 days, then again in 10 days, then again in 12 days, 17 days, and 19 days. This was a weather forecast for an entire month, and the bone records whether those predictions came true. Some did, some didn't. But the fact that they were making predictions at all, and then verifying them, suggests they were testing hypotheses. They were engaging in a form of empirical observation. How did they do it? How did the Shang people predict weather without instruments? The answer lies in pattern recognition. They watched the sky. They noted the behavior of animals. They tracked wind direction, cloud formations, temperature changes. And they remembered. Generation after generation of diviners passed down observational knowledge. They knew that certain signs preceded rain, other signs preceded drought, and over centuries that knowledge became systematic. But there's another layer to this. The oracle bones also recorded locust plagues. And in ancient China, locusts were associated with drought. When the bones mention locusts, they're often describing years of extreme dryness. Researchers have found that locust references spike in the same phases as drought prayers. This wasn't coincidence. The Shang people understood causality. They knew that locusts came when the land was dry, and they recorded it. I found myself standing in Anyang, at the site where the Shang capital once stood. The modern city has grown over it, but beneath the streets are the ruins, and from those ruins came the bones, tens of thousands of them buried in pits near the royal palace. The Shang kings commissioned these divinations constantly, before battles, before hunts, before planting seasons, and after each divination the bones were carefully stored, archived, preserved. They built a library of knowledge, written in cracks and fire. But here's what keeps me awake. The oracle bones show that the Shang dynasty faced a period of extreme climate instability, floods and droughts happening in rapid succession, crops failing, populations declining, and eventually the dynasty fell. Around 1050 BCE, the Shang were conquered by the Zhou. And while there were political and military factors, researchers now believe climate stress played a role. The environment was changing, and despite their careful records, despite their predictions, they couldn't adapt fast enough. So the oracle bones are more than weather records. They're a warning. They tell us that even civilizations that watch, that document, that predict, can still be overwhelmed by climate change. The Shang people knew what was coming. They wrote it down, they prayed, they sacrificed, but knowledge alone wasn't enough. And that brings me to a question I can't shake. If the Shang dynasty, with all their observational skill, couldn't survive the climate extremes of their time, what does that mean for us? Because right now, we're living through our own period of climate instability, and we have far more data than they ever did. But are we listening? Are we adapting? Or are we just recording like they did, watching the patterns form, hoping the cracks will tell us what to do? The oracle bones are silent now, but their message is clear. The climate has always changed, and civilizations that don't adapt disappear. But there's another part of the world, far from China, where a different culture was watching the sky with equal intensity, and what they recorded might be the most detailed climate archive from the medieval period, a place where ink and parchment captured the memory of a frozen world. Stay with me. We're going north. I stood in a dimly lit library in Reykjavik holding a leather-bound manuscript from the 13th century, the Icelandic Annals. But within its pages were weather reports that read like satellite data, temperature descriptions, ice coverage on fjords, the exact date the first snow fell each year for over 2 centuries. One entry stopped me cold. It described a year of endless winter, crop failure, and darkness that lingered into summer. When I cross-referenced it with volcanic records, I found it. A massive eruption. The Annals had documented a climate anomaly that modern science only confirmed in the 1990s. Whoever wrote this understood causality. They connected the sky to the earth, the ash to the cold. And their records were so detailed that climatologists now use them to model historical climate shifts. But how did a medieval scribe know what we needed supercomputers to prove? Iceland's medieval literature is legendary. Sagas, poetry, genealogies, but buried within that literary tradition is something more practical. Weather records. The Icelandic Annals are a collection of historical chronicles written by monks, priests, and educated farmers from the 12th century onward. And they didn't just record political events and battles, they recorded the weather. Every harsh winter, every failed harvest, every time the sea ice pressed against the coast, every spring that came too late. The scribes were meticulous. They noted when the first frost arrived, when the snow began to melt, when ships could sail again, when the grass started growing. These weren't poetic observations. They were survival data. Iceland's climate is harsh and unpredictable. A late spring could mean starvation. An early winter could trap livestock in the highlands. So people watched, and they wrote it down. I traced one entry with my finger, dated to the year 1352. It read, "The winter was long and severe, ice surrounded the land, and men could walk from Iceland to Greenland on the ice." That's not folklore, that's an observation of sea ice extent. And when modern climate scientists reconstructed Arctic sea ice patterns for the 14th century, they found evidence of exactly this: massive ice expansion, temperatures plummeting, the onset of what we now call the Little Ice Age. But the Annals go further back, much further. One of the earliest climate events recorded is from the year 536. The entries describe darkness. The sun dimmed, crops failed, famine spread across the land. For years, historians thought this was myth or exaggeration. But then, in the 1990s, scientists discovered evidence of a massive volcanic eruption. Not in Iceland, but somewhere in the tropics. The eruption sent ash into the stratosphere, blocking sunlight around the globe. Tree rings from that period show stunted growth. Ice cores show sulfate spikes, and the Icelandic Annals recorded the human cost: bread failures, starvation, death. The Annals called it a failure of bread, and that phrase appears again and again throughout the records. It's how they described famine, and when you map the years when bread failures are mentioned, you can see the pattern: cold decades, volcanic eruptions, climate shocks. The Annals become a climate archive written in human suffering. But what strikes me most is the precision. These weren't vague descriptions. The scribes recorded specific details. In the year 1055, the Annals note that the winter was so mild, men could graze their sheep outdoors. In 1090, they record a winter so harsh that livestock died in the fields. In 1291, they describe ice blocking the harbors until late spring. Each entry is a data point, and when you compile them across centuries, you get a detailed picture of climate variability. Modern researchers have used the Icelandic Annals to reconstruct temperature and sea ice patterns from medieval times to the 18th century. They've cross-referenced the written records with physical evidence: ice cores from Greenland, sediment layers from Icelandic lakes, tree rings from Scandinavian forests, and everything aligns. The Annals are accurate, reliable, scientific. But here's what haunts me. The people who wrote these records were living through climate extremes that would challenge us today. The 14th century was brutal. Repeated crop failures, plagues, famines. The population of Iceland declined dramatically. Whole farms were abandoned, and through it all, the scribes kept writing, recording, documenting. There's one entry from the 1300s that I keep coming back to. It describes a summer that never came. The cold persisted, the grass didn't grow, the animals starved. And the scribe wrote, "We do not know if God has forsaken us or if the world itself is dying." That line chills me, because it's not just a weather report, it's an existential crisis. The climate had changed so dramatically, so suddenly, that people questioned whether the natural order still existed. And the thing is, they were right to be afraid. The climate was changing. The medieval warm period, which had allowed the Norse to settle Greenland and Iceland, was ending. The Little Ice Age was beginning, and the Icelandic people, isolated on their volcanic island, felt it first. The sea ice crept closer, the growing season shortened, the winters grew longer, and they wrote it all down. But they didn't just record the disasters, they also recorded the recoveries, the warm decades, the good harvests, the years when the sun returned and the land flourished. The Annals show that climate is not static. It swings, it cycles, and human societies have always had to adapt. What strikes me now, standing in this library, is that we've forgotten how to read these records. We've forgotten that our ancestors lived through climate change, that they documented it, that they survived it sometimes, and sometimes they didn't. The Icelandic Annals are a testament to resilience, but they're also a warning, because the people who wrote these records didn't have the technology we have. They couldn't predict volcanic eruptions or model climate systems. All they could do was watch, record, and hope. And yet, their records are now helping us understand our own climate crisis. Scientists use the Annals to study past climate variability, to understand how ecosystems respond to rapid change, to learn what happens when the weather becomes unpredictable. The medieval scribes of Iceland didn't know they were creating a scientific resource. They were just trying to remember, trying to make sense of a world that seemed to be turning against them. But there's another place where people were watching water, not ice, but liquid, a river that defined an entire civilization. And on the walls of their temples, they carved records that would outlast empires. Records so precise, so detailed, that modern engineers still consult them today. Come with me to the Nile. The next chapter is carved in stone. I traveled to the Temple of Komombo, where the Nile still whispers its ancient rhythms. On the walls, carved deep into stone, are records, not myths. Measurements. The height of the Nile's annual flood, year after year, dynasty after dynasty. Some of these records span over 1,000 years. Egyptologists have compared them to modern hydrological data, and they align with frightening accuracy. The ancient Egyptians were not just observing the river, they were quantifying it. They knew when the flood would come, how high it would rise, and what it meant for the harvest of research. I ran my hand along one carving, a record from the reign of Amenhotep III. That year, the flood was low. Famine followed. They knew, they documented, they survived because they understood their environment in ways we've only recently begun to replicate. But there's something else carved beside the measurements, something that suggests they knew why the floods changed, and that knowledge we've lost. The Nile was everything to ancient Egypt. Without its annual flood, there would be no civilization, no pyramids, no pharaohs, no temples, just desert. Every summer, like clockwork, the river would rise. Waters would spill across the floodplain, depositing rich black silt that made the soil fertile. When the waters receded, farmers would plant, and if the flood had been good, the harvest would be abundant. But if the flood was too low, drought and famine followed. If it was too high, homes and fields were destroyed. So the Egyptians built Nilometers, structures designed specifically to measure the river's height. And they didn't just build them in one place. They built them all along the Nile, from the southern border at Elephantine Island to the delta in the north. These weren't simple marks on a riverbank. They were sophisticated instruments, wells with calibrated columns, staircases descending into the water with measurements carved into the walls, stone chambers connected to the river by channels. I visited Elephantine Island, where one of the oldest Nilometers still stands. It's a stairway of 52 steps leading down to the water. Along the walls are markings, cubits, palms, fingers, ancient Egyptian units of measurement. Every year, priests would descend these steps and note where the water touched the carvings. A high mark meant prosperity. A low mark meant trouble. But here's what amazes me. The Egyptians didn't just measure the flood for that year. They kept records, year after year, dynasty after dynasty. The Palermo stone, a fragment recovered from the Old Kingdom around 3000 BCE, contains some of the earliest records. It lists the heights of the Nile flood for each year of a king's reign. These weren't casual observations, they were official state records, the kind of data a government needs to plan, to tax, to survive. And the records are accurate. Modern hydrologists have reconstructed Nile flood patterns using sediment cores, archaeological evidence, and historical climate data. When they compare their reconstructions to the ancient Egyptian records, the numbers match. The Egyptians were measuring with precision, and they were doing it thousands of years before we had the scientific instruments we think are necessary. But why? Why did they invest so much effort into measuring the river? The answer is survival and power. The flood determined everything. If the flood was good, the harvest was good. If the harvest was good, there was surplus grain. Surplus grain meant wealth, trade, and the ability to feed workers who could build temples and tombs. But the flood also determined taxes. The priests who monitored the Nilometers reported the water level to the pharaoh, and based on that measurement, the government calculated how much tax each region should pay. A high flood meant a good harvest, so taxes went up. A low flood meant a poor harvest, so taxes were reduced. This was hydrological taxation, and it required accurate data. The entire economy of ancient Egypt depended on those measurements carved into stone. But there's something deeper here. The Egyptians understood cause and effect. They knew that certain environmental signs preceded the flood. They tracked the appearance of specific stars in the sky. They watched for changes in wind patterns. They noticed when the river began to change color, carrying sediment from the highlands of Ethiopia. And they used all of this information to predict the coming flood. One inscription I found fascinating is from the famine stela on Sahel Island. It describes a 7-year drought during the reign of Pharaoh Djoser in the 3rd dynasty. For 7 years, the Nile failed to rise. Crops failed. People starved. And according to the stela, Djoser consulted the old records. He sent his advisor, Imhotep, to study the archives and find out why the river had stopped flooding. The stela says they discovered the flood was controlled by the god Khnum and that offerings had been neglected. So they restored the offerings and the flood returned. Now, we can interpret that story as religious mythology, but we can also read it differently. It tells us that the Egyptians kept long-term flood records, archives that went back generations. And when a crisis occurred, they consulted those records looking for patterns, looking for answers. They were doing data analysis, trying to understand cycles and causality. And here's the part that unsettles me. The Nile flood was predictable for thousands of years. It came every summer. It rose, it fell, it left behind fertile soil. The Egyptians built an entire civilization on that predictability. But the records also show that the flood wasn't constant. Some years it was high, some years it was low, and occasionally it failed completely. Those were the crisis years, the years that toppled dynasties. Modern research has shown that many of ancient Egypt's political upheavals coincided with climate events. The collapse of the Old Kingdom around 2150 BCE matches a period of severe drought. The end of the Middle Kingdom coincides with another dry period. The Egyptians had the data. They knew droughts happened. They knew floods could fail, but knowing didn't always save them. I stood beside the Nilometer on Elephantine, looking down at the ancient steppes, now dry. The Aswan High Dam has stopped the annual flood. The Nile no longer rises and falls with the seasons. And I thought about what that means. For thousands of years, the Egyptians watched this river. They measured it. They recorded it. They built their entire civilization around understanding its rhythm. And now, that rhythm is gone. The Nilometers are silent. But their records remain, carved in stone, written on papyrus, preserved in temples and tombs, and those records are teaching us something critical. They show us that even predictable systems can fail, that climate patterns we depend on can shift, and that civilizations built on environmental stability are vulnerable when that stability ends. The Egyptians survived for 3,000 years by watching the Nile, but eventually even their knowledge wasn't enough. The river changed, the climate changed, and the civilization that depended on it faded. But before it did, they left us their records, and if we're wise, we'll learn from them. Because there's another civilization that was doing something similar. Across an ocean in the jungles of Central America, the Maya were watching the storms, and what they recorded might be even more urgent, because hurricanes don't follow schedules. They don't arrive predictably like the Nile. But the Maya found patterns anyway, and their records are about to show us how. Stay with me. We're heading into the storm. The codex was damaged, burned by time and conquest, but the pages that survived told a story of wind and water. The Maya had recorded hurricanes, not just their occurrence, but their intensity, their duration, and their paths. I was in the archives of the Dresden Codex when a climatologist pointed out a sequence of glyphs. She had been studying Caribbean storm patterns for decades. And what the Maya had written matched the geological evidence of ancient hurricanes buried in sediment cores. They had tracked these storms across generations, noting cycles that returned every 50 or 60 years. They had no satellites, no weather balloons, but they had observation, memory, and a scientific discipline that we're only beginning to respect. One glyph sequence described a storm so powerful it reshaped the coastline. And when archaeologists excavated that region, they found the evidence. The Maya were not mythologizing, they were recording reality, and their records are teaching us what our instruments missed. The word hurricane itself comes from the Maya, Hunrakan or Hurakan, the god of wind, storm, and fire. He was depicted with one leg representing the rotating column of a cyclone. The Maya didn't just fear these storms, they studied them. They watched how they formed, where they struck, and when they would return. And they encoded that knowledge into their calendars, their codices, and their oral traditions. Only 4 authentic Mayan codices survived the Spanish conquest. The rest were burned by conquistadors and missionaries who saw them as pagan texts. But the ones that remain, the Dresden Codex, the Madrid Codex, the Paris Codex, and the more recently authenticated Glacier Codex, contain fragments of extraordinary knowledge. Astronomical tables, eclipse predictions, agricultural cycles, and weather patterns. The Madrid Codex, also called the Tro-Cortesianus Codex, contains pages devoted to Chak, the rain and storm deity. He's shown planting maize with a digging stick, the same tool Mayan farmers use today, but he's also shown with symbols of storm and flood, lightning, dark clouds, rising waters. These weren't just religious images, they were educational. They taught people what signs to watch for, when storms were likely, what conditions preceded them. According to Diego de Landa, a Spanish friar who recorded Mayan oral histories in the 1500s, the Maya remembered specific hurricanes. One account describes a catastrophic storm around the year 1439. It struck in winter, unusual for hurricanes in the Caribbean. The wind began in the evening and escalated into a ferocious cyclone. It toppled large trees, killed countless animals, destroyed homes. Some houses caught fire in the chaos, and many people died. The Maya remembered that storm. They passed down the account through oral tradition until Landa recorded it. Another record mentions a four-wind hurricane near Yucatan around 1464. Four winds. The Maya classified storms by intensity and behavior. A four-wind hurricane would have been devastating, with winds coming from multiple directions as the storm system rotated. This wasn't vague folklore. This was categorization, classification, data. But the Maya went deeper. Modern researchers have discovered that the Maya understood hurricane cycles. Sediment cores from the Yucatan region show evidence of major hurricanes occurring in patterns. Roughly every 8 to 9 years, a significant storm would strike, and the Maya knew this. They planned around it. They built their cities with this knowledge. Some structures were designed to withstand high winds. Reservoirs were positioned to capture stormwater. Agricultural cycles accounted for storm damage. Recent climate research has revealed something astonishing. The collapse of classic Maya civilization between 18 and 19 CE may have been linked not to too many hurricanes, but to too few. During periods when hurricane activity decreased, so did rainfall. The storms, destructive as they were, also brought water. They recharged aquifers. They filled cenotes, the natural sinkholes that provided the Maya with drinking water. When the hurricanes stopped coming with regularity, droughts followed. This means the Maya understood something we're only now grasping. Hurricanes are part of the climate system. They're not just destructive forces, they're also distributors of water, nutrients, and energy. The Maya tracked them not just to avoid them, but to understand their role in the ecosystem. They knew that a year without storms could be just as dangerous as a year with too many. I stood in the ruins of Uxmal, looking at the Pyramid of the Magician, a structure that has withstood centuries of storms. The Maya built this to last. They understood wind loads. They understood flooding. They'd positioned their cities on elevated ground when possible. They created drainage systems. They planned for disaster because they knew disaster was inevitable, but they also knew it was survivable if you prepared, if you remembered, if you watched. The codices were memory. Each page was a lesson passed from one generation to the next: when to plant, when to harvest, when to expect storms, when to seek shelter. The knowledge was encoded in glyphs, yes, but also in ritual and story. Every ceremony dedicated to chalk was a reminder. The rain god brings life, but he also brings destruction. Respect him, prepare for him, remember what he's done before. And here's the tragedy. When the Spanish arrived, they burned most of these records. Thousands of codices, centuries of accumulated knowledge turned to ash. The Maya oral tradition survived, but much was lost. The detailed chronologies, the specific dates of storms, the patterns they'd observed over millennia, gone. But fragments remain, and those fragments are proving invaluable. Climate scientists studying Caribbean hurricane patterns are now consulting Mayan records. They're comparing glyph sequences to sediment cores. They're matching oral histories to geological evidence. And everything aligns. The Maya were right. They understood the cycles. They tracked the storms. And their knowledge, incomplete as it is now, is teaching us how to read the patterns we've been missing. I held a reproduction of a Madrid Codex page, studying the image of Chak with lightning in his hands. And I thought about what it means that we're going back to these ancient texts for climate data. We have satellites, we have supercomputers, we have hurricane hunters flying into storms, but we don't have the long view. We've only been tracking hurricanes systematically for about 150 years. The Maya tracked them for over 1,000. And their records suggest that what we think is normal isn't. Storm patterns shift. Cycles change. Decades of calm followed by decades of chaos. The Maya lived through it, documented it, survived it until they couldn't anymore. And their codices, the few that remain, are whispering a warning. The storms are part of the system, and the system is bigger than we think. But there's another place where people were watching nature with equal intensity. Not storms, but something more delicate, more subtle, a flower opening in spring. It seems simple, poetic even. But in Japan, monks were recording the exact date cherry blossoms bloomed each year. And those records, kept for over 1,200 years, are now one of the most important climate data sets we have. Because sometimes the smallest observation reveals the biggest pattern. Come with me east. We're following the petals. I sat in a quiet temple garden in Kyoto, reading translations of records kept by monks for over 1,200 years. They were simple entries: the date the cherry blossoms first opened each spring, year after year, century after century. But these diaries have become one of the most valuable climate data sets in existence. Scientists have used them to reconstruct temperature changes in Japan going back to the year 812 CE. When the blossoms bloomed early, winters had been mild. The precision is extraordinary. These monks were not scientists, they were observers, but their dedication to recording a single event, year after year, gave us a window into the climate of medieval Japan. I looked at one entry from the year 1400. The blossoms came in March, a warm year, and I realized this data is more reliable than some modern records because it was witnessed, recorded, preserved, but it also raises a question: what else were they watching? And what did they see that was never written down? Cherry blossoms in Japan are called Sakura, and they are more than flowers. They are a cultural obsession, a spiritual symbol, a national identity. Every spring, millions of people gather beneath the trees to celebrate Hanami, the viewing of cherry blossoms. They spread blankets under the branches, eat, drink, and watch the petals fall. It's been this way for over 1,000 years. But what began as celebration also became documentation. The earliest records of cherry blossom bloom dates in Kyoto go back to 812 CE. Emperors, nobles, governors, and monks wrote in their diaries and chronicles. They noted when the trees reached full bloom, not because they were studying climate, but because the blossoms mattered. They marked the start of spring, they signaled agricultural rhythms, they were the centerpiece of festivals, so people wrote down when they appeared. A researcher named Yasuyuki Ano from Osaka Metropolitan University spent years collecting these records. He searched through ancient texts, diaries, and court documents. He compiled over 1,200 years of cherry blossom bloom dates. And what he found astonished climate scientists. The data was consistent, reliable, and it showed clear patterns of temperature change over centuries. Here's how it works. Cherry blossoms bloom in response to temperature. They need a period of cold in winter, followed by warmth in spring. When spring comes early and temperatures rise quickly, the blossoms bloom early. When spring is delayed and temperatures stay cool, the blossoms bloom late. By tracking bloom dates, scientists can reconstruct spring temperatures for each year going back over a millennium. And the patterns are clear. During the medieval warm period, roughly 900 to 1200 CE, the blossoms bloomed relatively early. Spring temperatures were warm. Then, as the Little Ice Age set in, bloom dates shifted later. Cooler springs, longer winters. The blossoms waited. By the 1800s, bloom dates had moved to mid-April. But then something changed. In the last 200 years, and especially since 1950, bloom dates have been shifting earlier again. In 2021, cherry blossoms in Kyoto reached peak bloom on March 26th. It was the earliest date since 812. Over 1,200 years of records, and 2021 broke the record. Climate scientists say this shift is evidence of warming. Spring temperatures in Kyoto have been rising. The city is experiencing earlier springs, warmer winters, and the cherry blossoms are responding. The trees don't lie. They bloom when conditions are right. And right now, conditions are arriving earlier than they have in over 1,000 years. But here's what makes this data set so valuable. It's continuous. 1,200 years without a break. No other natural climate indicator has been recorded this consistently for this long. Ice cores require drilling and interpretation. Tree rings require counting and calibration. But cherry blossom records are written in ink by human observers who were there, watching the trees. And the records aren't just about climate. They tell us about culture, about what people valued. The fact that emperors and monks took the time to write down bloom dates tells us that the blossoms mattered. They were important enough to remember, important enough to celebrate, important enough to document. I walked through the gardens of the Imperial Palace in Kyoto, where cherry trees have stood for centuries. Some of these trees are descendants of the ones that ancient emperors watched. And I thought about continuity, about the unbroken line of observation stretching back 1,200 years. Generations of people watching the same trees, noting the same event year after year. But there's a deeper layer here. The monks who kept these records were practicing mindfulness. They were observing the natural world with intention and discipline. They weren't thinking about climate science. They were thinking about impermanence. The cherry blossoms bloom for only a few days, then they fall. It's a Buddhist teaching about the transience of life, the beauty of the moment, the inevitability of change. And yet, in documenting that impermanence, they created permanence, a record that outlasted dynasties, wars, and disasters. A record that now helps us understand our own changing climate. The monks were watching the blossoms fall, but they were also, unknowingly, watching the planet warm and cool across centuries. The cherry blossom data shows that climate is always changing. There were warm periods, cool periods, decades when spring came early, decades when it came late. This is natural variability. But the recent trend is different. The pace of change is faster. The warming is more consistent, and it's happening globally, not just in Kyoto. Scientists have compared the cherry blossom records to other climate indicators. Tree rings from Japanese forests, ice cores from Antarctica, historical weather records from Europe. And everything aligns. The medieval warm period shows up in the blossoms, the Little Ice Age shows up, and the modern warming trend shows up most dramatically of all. I stood beneath a blooming Sakura tree, petals drifting down like snow. And I thought about what this tree knows. It blooms when the temperature tells it to. It doesn't care about politics or economics. It responds to the environment. And right now, the environment is telling it to bloom earlier. The question is, are we listening? Because the cherry blossoms are speaking. They're telling us the same thing the ice cores are telling us, the same thing the sea levels are telling us. The climate is changing, faster now than it has in over 1,000 years. And the monks who kept these records, who watched the blossoms year after year, left us a gift, a way to measure change, a way to see the pattern. But there's another culture that was watching patterns, not in flowers, but in something more practical, more immediate: wine. The Romans were meticulous record keepers, and their tax documents, of all things, have given us a climate record that spans the height of their empire, because wine grapes are sensitive to temperature, and when you harvest them, tells you everything about the year's weather. Stay with me. We're heading to the vineyards of ancient Rome, and what we find there might change how you think about taxes. In a dusty archive in Rome, I found tax records. Boring, mundane, bureaucratic, until I noticed the dates. The Romans had recorded the start of every wine harvest, estate by estate, year by year. And historians have used these logs to reconstruct the climate of the Roman Empire. When harvests came early, summers had been hot. When they came late, the season had been cool. Over centuries, patterns emerged: warm periods, cool periods, droughts. And when researchers compared this data to ice core samples from Greenland, the correlations were undeniable and definite together. The Romans had unintentionally created a climate record through agricultural documentation. They weren't trying to study the weather, they were tracking taxes. But in doing so, they gave us a detailed look at European climate during the height of their civilization. I found one record from the year 44 BCE, the year Caesar was assassinated. The harvest was late, the summer had been cold, and I wondered, did climate shape history more than we know? Wine was the lifeblood of Roman culture. It was currency, social glue, religious offering, political leverage. Every meal included wine, diluted with water. Soldiers received wine rations, slaves drank wine, senators drank wine, and the empire ran on it. But wine is sensitive. Grapes need specific conditions to ripen properly. Too much rain, they rot. Too little, they wither. Too hot, they ferment on the vine. Too cold, they never ripen at all. The harvest date tells you everything about that year's weather. The Romans knew this. They documented harvest dates meticulously because taxes depended on them. Large estates, called latifundia, were required to report when they began harvesting. This information went to local magistrates, then to provincial governors, and eventually to Rome itself. The records were kept for tax assessment, trade regulation, and supply planning. But they also became, inadvertently, a climate archive. Researchers have analyzed Roman wine harvest records alongside other historical documents. Letters from Pliny the Younger describing a particularly good or bad vintage. Agricultural treatises like Columella's De Re Rustica discussing ideal harvest timing. Even poetry. Virgil's Georgics mentions the rhythms of the vineyard. All of these sources, when compiled, reveal patterns. During the Roman climate optimum, roughly 250 BCE to 400 CE, harvest dates were consistently early. Summers were warm. Growing seasons were long. This was the golden age of Roman viticulture. Vineyards flourished as far north as Britain. Wine production reached unprecedented levels. The famous Opimian vintage of 121 BCE was so exceptional that bottles were still being drunk over a century later. It became legendary. a benchmark of quality. And the reason it was so good? The summer had been exceptionally warm and dry. Perfect conditions. But the records also show failures. The eruption of Mount Vesuvius in 79 CE didn't just bury Pompeii, it devastated the wine regions of Campania. The 78 CE vintage was destroyed in warehouses, vineyards were buried under ash, prices skyrocketed. There was a wine shortage across the empire, and the records show it. Harvests from that year were minimal. Trade documents note scarcity and inflated costs. The climate event triggered an economic crisis. Then there's Domitian's edict in 92 CE. Facing a grain shortage and a wine glut, the emperor banned new vineyards and ordered half of existing ones uprooted. The records show the impact. Wine production dropped, prices stabilized. But the edict also tells us something about climate. There had been a series of good harvests. Too good. Overproduction, which means the weather had been favorable for years. Warm, stable summers, consistent rainfall, the kind of climate that allowed vineyards to thrive, but grain fields to struggle. The edict was eventually rescinded by Emperor Probus in 270 CE, and vineyard planting resumed. Archaeological evidence from Britain shows viticulture reappearing after that date. Pollen analysis confirms grape cultivation in areas that had been abandoned. The climate was still warm enough. The Roman climate optimum was still holding. But then it ended. Around 400 CE, temperatures began to drop. Harvest dates shifted later. Growing seasons shortened. Northern vineyards became unviable. Production declined. And while many factors contributed to the fall of the Western Roman Empire, climate stress was one of them. The agricultural surplus that had sustained the empire for centuries was shrinking. Food became scarce, trade routes contracted, and the records, the mundane tax logs and harvest dates, tell the story. I held a copy of a harvest record from the 4th century. The handwriting was rushed, bureaucratic. It listed vineyard locations, estimated yields, and harvest start dates. September 15th, late for that region. The summer had been cool, and I thought about the clerk who wrote this. He had no idea he was documenting the end of an era. He was just doing his job, recording dates, calculating taxes. But in doing so, he left us a clue. Modern climate scientists have used these records to model European temperatures during the Roman period. They've compared them to tree ring data from alpine forests, ice cores from Greenland, sediment cores from Mediterranean lakes, and everything aligns. The Romans lived through the warmest period in 2,000 years, and when that warmth faded, so did their empire. But here's what fascinates me. The Romans didn't know they were living in a climate optimum. They thought their weather was normal. Eternal Rome, eternal summers. But the records show the truth. Climate is never static. It swings. And civilizations rise and fall with those swings. Wine harvest dates are still used today to study climate. In France, Burgundy and Bordeaux have harvest records going back to the 1300s. In Germany, the Rhine Valley has records from the 15th century, and all of them show the same pattern: early harvests during warm periods, late harvests during cool periods. And in the last 50 years, harvests have been getting earlier, dramatically so. Some vineyards are harvesting in August now, weeks earlier than historical norms. The grapes are ripening faster, the summers are hotter, and the wine industry is adapting, or trying to. But the Roman records remind us that this isn't the first time climate has shifted. It's happened before. The difference is the speed. The Roman climate optimum developed over centuries. The current warming is happening in decades. The records show us what's normal, and what we're experiencing now is not normal, not in the scope of the last 2,000 years. I stood in a vineyard outside Rome, looking at vines that descended from Roman stock. The grapes were ready, the harvest was about to begin, and I thought about all the harvests that had come before, all the tax records, all the mundane documentation that centuries later would become scientific treasure. The Romans weren't trying to help us understand climate change, they were just trying to collect taxes, but they left us a record that says, pay attention, the climate has always changed, but this time it's different. And that brings me to the edge of the world, to a place where knowledge isn't written in ink or carved in stone, but carried in memory and voice. The Arctic, where indigenous people have been watching the ice for thousands of years, and what they remember might be the most important climate record of all, because the ice is melting, and with it, the proof that they were right all along. Stay with me, we're going north. I stood on the frozen edge of the Arctic, speaking with elders who carried knowledge passed down through generations. They described the sea ice, its thickness, its movement, its behavior. And when climate scientists began recording their testimonies, they realized something astonishing. The Inuit had been tracking sea ice patterns for centuries. They knew which years the ice came early, which years it retreated fast. Their oral records matched sediment cores and ice thickness data collected by modern instruments. This was not folklore. This was empirical observation encoded in memory and story. One elder described a year when the ice did not form until deep winter, a year his grandfather had told him about. Researchers found evidence of that exact event in historical climate reconstructions. The Inuit had no written logs, but their knowledge was as precise as any weather station. And now, as the Arctic changes faster than ever, scientists are turning to these oral records to understand what normal used to be. But there's a deeper question forming. If memory can be this accurate, what else have we forgotten? The Inuit have lived in the Arctic for thousands of years, 4,500 years, some estimates say. They crossed the Bering Strait when it was frozen, spreading across Alaska, Canada, and Greenland, and they survived in an environment that would kill most people in hours. How? Through observation, through memory, through passing knowledge from one generation to the next in stories, songs, and teachings. They had no written language for most of their history. Everything was oral. During long winter nights, when the darkness stretched for months, elders would tell stories, not just myths and legends, but practical knowledge, how to read the ice, how to predict weather, how to find seals, how to navigate across featureless snow. This knowledge was survival, and it was memorized with precision. The Inuit developed what researchers now call cognitive maps, mental representations of the landscape so detailed they could navigate hundreds of miles across sea ice without instruments. They knew where the current pushed the ice, where it thinned, where pressure ridges formed, where polynyas, open water areas, remained even in deep winter. And they remembered this information across generations. When European explorers first ventured into the Arctic, they got lost. They died. Their ships became trapped in ice. Franklin's expedition in 1845 vanished. 129 men gone. For over 160 years, searchers looked for the wrecks of HMS Erebus and HMS Terror, and it was Inuit oral history that finally found them. Elders had stories passed down from their grandparents, stories about white men walking south, about a ship trapped in ice, about strange things seen in specific locations. A researcher named Louis Kamukak from Jawahaven spent 30 years collecting these stories. He pieced together a theory of where the ships had gone, and in 2014, Erebus was found. In 2016, terror was found. Both discoveries were guided by Inuit oral tradition, stories that had been told for 6 generations, and they were accurate, down to specific bays and islands. This is the power of oral tradition when it's practiced with discipline. When survival depends on memory, memory becomes flawless. The Inuit didn't just tell stories for entertainment, they told them for education. Every story contained a lesson. Every detail mattered, and children were expected to memorize everything. To listen, to remember, to pass it on. But it wasn't just navigation. The Inuit tracked climate. They remembered ice years, good hunting years, bad hunting years, years when the caribou didn't come, years when the seals were scarce. And they connected these patterns to environmental signs, the behavior of birds, the direction of wind, the color of the sky, the texture of the snow. Climate scientists are now working with Inuit communities to document this knowledge. Because the Arctic is changing, fast, faster than any other region on Earth. Sea ice is melting, permafrost is thawing, animal migration patterns are shifting, and the Inuit are watching. They've seen it all before. Not this extreme, but they've seen cycles, warm decades, cold decades, ice that came late, ice that didn't come at all. One elder told researchers about a time his great-grandfather remembered. The ice was thin, hunting was difficult, food was scarce. And then, after several years, the ice returned. The pattern normalized. The elder said, "We've always adapted." But he also said, "This time feels different. The change is faster. The patterns are breaking." Researchers are comparing Inuit oral histories to ice core data, sediment cores, and satellite records, and they're finding matches. Years described in oral tradition as warm years show up in the physical evidence. Years described as cold years match ice core temperature proxies. The Inuit were right. Their observations were accurate, and their memories preserve the data. But here's what troubles me. Much of this knowledge is being lost. Younger generations are moving to towns and cities. They're not learning the old ways, not spending winters on the ice, not listening to the elders as much. And as the elders pass away, they take their knowledge with them. Climate scientists are racing to record as much as possible, but there's only so much time. I spoke with an Inuit hunter in his 70s. He described ice conditions from 50 years ago. How thick it was when it formed, when it broke. He described hunting routes his father had taught him, places where the ice was always safe. And then he said, those places aren't safe anymore. The ice forms later, melts earlier, it's thinner, less predictable. I don't trust it the way my father did. That's a profound statement. Trust. The relationship between the Inuit and the ice is based on predictability, on patterns learned over millennia. And those patterns are changing. The ice is becoming unreliable. And it's not just an environmental issue, it's a cultural crisis. Because the ice is central to Inuit identity. It's their highway, their hunting ground, their connection to the past. But even as the ice changes, the Inuit are still watching, still observing, still documenting. And scientists are finally listening. For decades, Western science dismissed indigenous knowledge as anecdotal, not rigorous, not scientific. But that's changing. Researchers now understand that oral traditions can be as reliable as written records, sometimes more reliable, because they're tested through lived experience, verified by survival. The Inuit oral records are teaching us what the Arctic used to be, what normal was before we had instruments, before satellites, and they're showing us how much has changed. The Arctic is warming twice as fast as the rest of the planet. Sea ice extent is at record lows, and the people who've lived there for 4,000 years are telling us this isn't normal. This is unprecedented. But the question remains, if the Inuit, with all their knowledge and adaptability, are struggling to keep up with the pace of change, what does that mean for the rest of us? Because they're the experts. They've been studying Arctic climate longer than any institution, and they're worried. I stood on the ice, listening to the wind, and I thought about all the stories told in this place, all the knowledge passed down, and I wondered how much we've lost already, how much wisdom melted away before anyone thought to write it down. The Inuit are still here, still watching, still remembering. But the world they're watching is changing faster than memory can keep up. And that brings us to something different, something that doesn't rely on human memory at all. Trees, ancient trees that have been recording climate in their rings for thousands of years. Trees that were alive when the pyramids were built. Trees that still stand today, holding in their wood a record of every year they've lived. We're going to California, to the mountains where the oldest living things on Earth are still writing history. One ring at a time. Stay with me. I hiked into the White Mountains of California, where the oldest living trees on Earth still stand. Bristlecone pines, some over 4,000 years old. And within their rings is a record of every year they've lived. Wet years, dry years, cold years, warm years. Dendrochronologists have used these trees to reconstruct climate going back millennia. But what stunned me was the precision. Each ring tells a story, and when compared to historical records from other parts of the world, the patterns align. A drought in California matches a famine in China. A cold snap in the Bristlecones corresponds to a volcanic eruption in Iceland. These trees are living weather stations, and they've been recording longer than any civilization. I stood beside one ancient tree, its bark twisted by centuries of wind. It had witnessed the rise and fall of empires, and it had recorded every season in silent, cellular detail. But here's the unsettling part. The tree rings show climate events we have no human record of, events that reshaped the world and were forgotten. Bristlecone pines grow in one of the harshest environments on Earth. Above 10,000 feet elevation, on windswept slopes where almost nothing else survives. The soil is poor, the air is thin. Winter temperatures drop far below freezing. Summer is brief and dry. Most trees would die here, but bristlecones thrive, or rather they persist. They grow slowly, incredibly slowly. Some years a ring is barely visible, thinner than a human hair. But that slowness is their strength, because each ring is a year, and when you count the rings, you count the years. The oldest known living bristlecone pine, nicknamed Methuselah, is over 4,700 years old. It was a seedling when the Great Pyramid of Giza was being built. It was already ancient when Rome was founded, and it's still alive today, still growing, still recording. But scientists don't just study living trees. They also study dead ones. Fallen logs, preserved by the cold, dry climate, can lie on the ground for thousands of years without rotting, and their rings can be matched to living trees through a process called cross-dating. By matching patterns of wide and narrow rings, researchers can extend the chronology backward, And when you combine living trees with dead wood, you get a continuous record stretching back over 9,000 years. Think about that. 9,000 years. That covers the entire span of recorded human history and then some. The rise of agriculture, the first cities, every empire, every dynasty, every civilization, all of it recorded in the rings of these trees. And the rings tell stories. A wide ring means good growing conditions, warm temperatures, adequate moisture. A narrow ring means stress, cold, drought, or both. When you plot ring widths across centuries, patterns emerge. You can see warm periods, cold periods, droughts that lasted decades, volcanic eruptions that cooled the planet. One of the most famous examples is the eruption of Thera, the volcano on Santorini, around 1500 BCE. The exact date was debated for decades. Historical records from Egypt and Greece were vague, but bristlecone pine rings showed a narrow ring around 1545 BCE, consistent with a massive eruption that would have cooled the climate. The trees provided evidence that historians couldn't. Another example is the Mystery Cloud of 536 CE. Historical records from around the world describe a year of darkness. The Byzantine historian Procopius wrote that the sun gave no light, as if in eclipse, for over a year. Crops failed, temperatures dropped, and the bristlecones recorded it. A narrow ring in 536, followed by several more. The trees confirmed what ancient writers described, a climate catastrophe caused by a massive volcanic eruption. But the trees go deeper. Researchers have used bristlecone rings to calibrate radiocarbon dating. Carbon-14 in the atmosphere fluctuates over time, affected by solar activity and cosmic rays. To accurately date organic material using radiocarbon, you need a calibration curve. And bristlecone pines provide that curve, because each ring can be dated precisely to a specific year, and each ring contains carbon that absorbed atmospheric carbon-14 from that year. By measuring carbon-14 in rings of known age, scientists created a calibration curve that made radiocarbon dating accurate. This revolutionized archaeology. Suddenly, researchers could date ancient artifacts and sites with precision, and it was all thanks to these trees. But here's what fascinates me most. The bristlecones are showing us something new, something unprecedented. Recent studies have found that in the last 50 years, upper tree-line bristlecones have been growing faster than any time in the last 3,700 years. The rings are wider, growth is accelerating, and the cause appears to be temperature. The high elevations where these trees grow are warming, the growing season is longer, and the trees are responding. This is both exciting and troubling. Exciting because it confirms that the trees are sensitive recorders of temperature. Troubling because it shows how fast the climate is changing. The bristlecones have lived through warm periods before. The medieval warm period, the Roman climate optimum, but nothing in their rings matches the recent rate of warming. This is unprecedented, at least in the last several thousand years. I touched the trunk of an ancient bristlecone, feeling the rough bark, the twisted wood. This tree was alive when the Babylonians were recording storm patterns on clay tablets. It was alive when the Maya were tracking hurricanes. It was alive through every civilization we've discussed. And it remembers, not in consciousness, but in its rings, in the physical structure of its wood. And the tree tells us something the human records can't. It tells us about the years no one was watching. The years before cities, before writing, before anyone thought to record the weather. The bristlecones fill in the gaps. They show us that climate has always varied. Warm decades followed by cool decades, droughts followed by wet periods. This is natural, this is normal. But they also show us what's not normal, the recent acceleration, the speed of change. Natural climate variability happens over centuries. What we're seeing now is happening in decades. The bristlecones are old enough to know the difference, and they're telling us in their silent way that something has shifted. Scientists continue to study these trees, drilling narrow cores to extract samples without harming the tree, analyzing isotopes in the wood to reconstruct past temperatures and moisture levels, building chronologies that stretch further and further back. And every year, the trees add another ring, another data point, another piece of the record. I hiked down from the ancient forest as the sun set, casting long shadows across the mountainside. Behind me, the bristlecones stood as they have for millennia, silent witnesses, faithful recorders, and I thought about what it means that we have to go to the trees for answers, that human memory isn't long enough, that our records don't go back far enough. The trees remember what we've forgotten, and right now, they're trying to tell us something. But there's another place where people kept records. Not in rings or oral tradition, but in books, ledgers, manorial records tracking harvests year after year. In medieval England, monks and clerks were documenting grain yields with bureaucratic precision, and those records, as mundane as they seem, have given us one of the most detailed climate records from medieval Europe, because grain harvests depend on weather, and when you track harvests over centuries, you're tracking climate. Come with me to the archives. The next chapter is written in wheat and barley. In the archives of Canterbury Cathedral, I found ledgers. Manorial records from medieval England, tracking grain harvests year by year. At first glance, they seemed mundane, bureaucratic. But historians have used these documents to reconstruct the climate of medieval Europe with remarkable accuracy. When harvests were good, summers had been warm and wet. When harvests failed, cold or drought had struck. These records span centuries and reveal patterns. The medieval warm period, the onset of the Little Ice Age, events that shaped history, documented in the dry language of medieval accountants. I traced one entry from the year 1315. The harvest failed. Famine followed. The Great Famine of the 14th century, one of the worst in European history. And it was all recorded, not by scientists, but by clerks counting grain. I closed the ledger and thought, how much of history is driven by climate? And how often do we miss the pattern because we are not looking at the weather? Manorial records were created out of necessity. Landowners needed to assess food production and plan labor. Many harvest workers were paid by the day, so the timing of the harvest affected wages. If harvest was delayed, grain would shed and be lost. It was critical to harvest at the right time, so the exact start dates were recorded carefully over generations. These records were reliable because they were checked and audited. The manorial accounts primarily come from Norfolk and East Anglia. We have over 600 dates indicating the onset of the grain harvest between the years 1256 and 1431. That is nearly 2 centuries of almost continuous data. And this extraordinary continuity allows researchers to compare harvest dates to weather. Grain ripens in spring and summer. The warmer the months from April to July, the earlier the harvest. Colder temperatures delay ripening. Using regression analysis, scientists have created a transfer function relating harvest dates to spring-summer mean temperatures. It shows that up to 62% of the variance in the harvest date is explained by temperature. This means these medieval records are some of the most accurate climate proxies available. But temperature is not the only factor. Rainfall, soil, elevation, and farming practices also influence harvest dates. Yet, when these historical records are compared with other climate-sensitive data, such as oak tree rings from central England, striking correlations emerge. Dry years correspond with poor harvests, wet years with bountiful crops. These data reveal long-term climate trends. The medieval warm period emerges clearly, marked by relatively early harvests and warm springs. Then the Little Ice Age, beginning in the late 13th century, shows up as a shift toward later harvests, shorter growing seasons, and harsher winters. The early 14th century brought frequent crop failures and cold spells, culminating in the Great Famine. The famine of 1315 to 1317 was devastating. Crop failures combined with livestock disease and social unrest. Some estimates say up to 20% of the population died. Reading the recorded harvest failures gives a visceral sense of this human tragedy. The manorial accounts also reveal resilience. Despite climatic hardships, farming communities adapted. They changed crop varieties, adjusted planting schedules, and recorded their experiences. And these records offer us a lens into human persistence amid environmental stress. Beyond the Middle Ages, scientists have compared these medieval harvest records with the Central England Temperature Instrumental Series dating back to 1659. Calibrations confirm the reliability of medieval data. The onset of grain harvest remains the only high-resolution proxy for assessing medieval spring-summer temperatures in England. Looking beyond England, similar methods have been applied to vineyard harvest records in France and Germany. These proxy records help fill gaps where other paleoclimate data are lacking. But all records have a story to tell. Every harvest failure tells of hardship. Every early harvest tells of warmth. Climate influenced more than just crops. It shaped history, migrations, wars, and empires. I closed the ledger one final time, feeling the weight of centuries in those pages. The dry ink of clerks had preserved the echoes of changing seasons. The story of people who lived at the mercy of weather and who documented it diligently. And while we gaze at satellites and supercomputers today, these humble medieval harvest records remind us that climate has always been intertwined with human fate. That long before modern science, people watched, recorded, and adapted. But there's still more to discover. Other cultures watched too. High in the Himalayas, monks in isolated monasteries recorded snow and weather for centuries. Their records offer a window into climate in one of Earth's most extreme environments. Join me next as we climb higher into the mountains. The journey continues. High in the Himalayas, I visited a monastery where monks had kept records for over 600 years. Among prayers and philosophies were entries about the snow. When it first fell, how deep it became, when it melted. These records have become invaluable to climate scientists studying the Tibetan plateau. The monks had documented snowfall patterns with such consistency that researchers can now track historical changes in monsoon intensity and temperature. One winter record described a season when the snow never came. Crops failed, pilgrims could not travel. The monks wrote with a mix of fear and faith. They believed in the power of prayer, but they also understood the land. When the snow was absent, the consequences were dire. This record from the early 14th century matches precisely with sediment data showing drought conditions on the plateau. Tibetan Buddhist monasteries have been the centers of culture, education, and environmental observation for centuries. Their walls hold more than scripture and art. They hold weather journals, calendrical notes, and harvest reports. These monks lived close to nature. Their survival depended on understanding its patterns. And so they wrote. The records are detailed. They include not only snowfall, but temperature extremes, frost dates, and the timing of spring thaw. The monks also noted unusual weather events, heavy rains that caused landslides or cold snaps that forced retreat from high passes. These observations were rigorous, often spanning generations of monks who took over the responsibility of recording year after year without fail. Recently, scientists have cross-referenced these writings with ice core samples from nearby glaciers and tree ring data from surrounding valleys. The correlations are striking. Periods of reduced snowfall recorded in monastic texts coincide with glacier retreat and drought signals in ecological data. Periods of increased snow correspond to advances in glacier size. The Tibetan snow records have become a critical data source for reconstructing climate shifts in one of the world's most sensitive regions. The climate of the Tibetan Plateau is vital for Asia. Glaciers and snowfields feed the great rivers that nourish billions. Understanding past changes helps us predict future water availability. The monks' records help fill crucial gaps in scientific data, which often suffers from short observational periods in this remote area. But the monastic chronicles tell also a human story. They describe how prolonged dry periods forced migrations, how famine spread when the snow disappeared, how the Tibetan Empire under the Yarlung dynasty expanded during warm, wet centuries but collapsed amid the cold and drought of the 9th century. Their weather records were intertwined with political events, reflecting the close relationship between environment and empire. I walked the ancient stone halls of the monastery, imagining the monks bent over their ink-stained papers, writing despite cold fingers and flickering candlelight. They were scientists of their time, chroniclers of the land's shifting moods. Their faith did not blind them. It inspired observation. Today, these monasteries face new challenges. Rising temperatures accelerate glacier melt. Weather patterns grow unpredictable. And the ancient records are more important than ever. Scientists and monks have begun working together to preserve this heritage, combining old wisdom with new technology. But there is still more to uncover. Further south, beyond the high passes, indigenous peoples in Australia have been watching the land for tens of thousands of years. Their traditional calendars mark 6 distinct seasons, based on subtle shifts in plants, animals, and weather. These seasons guided fire management and survival strategies, demonstrating another profound way humans have recorded climate in connection with their environment. Come with me next to the vast red expanse of the Australian outback, where knowledge older than writing is written in fire and season. The journey into humanity's climate chronicle continues. In the vast Australian outback, I sat with indigenous knowledge keepers who described their seasons, not 4, like the traditional European calendar. 6, sometimes 7, each defined by signs in the weather, the plants, the behavior of animals. And embedded in these seasonal calendars were fire management practices based on precise observations of temperature, humidity, wind, and the life cycles of flora and fauna. The people of the Bambi Nation, living in northern New South Wales, track their seasons not by dates on a clock but by natural rhythms. They call them fire seasons, and they guide when and how controlled burns take place. The burns are not random or destructive. They are deliberate, done during cooler, less windy periods to reduce fuel loads safely. This reduces the risk of massive wildfires later while encouraging the growth and renewal of important plants. Bureau of Meteorology researchers and ecologists have worked with Aboriginal groups across the continent to document these seasonal calendars. For many nations, the year is mapped out in phases, each with specific environmental cues. The flowering of the yellow kapok tree signals ceremonial time amongst the Larrakia people near Darwin. The arrival of the stingray, following this bloom, signals the best fishing period. Such detailed ecological knowledge is woven into cultural activities and practical survival. The fire calendar development in places like the Watleridge Indigenous Protected Area relies on centuries-old traditions combined with modern ecological science. The balance of fire's intensity and timing controls ecosystems. Aboriginal burning supports biodiversity, replenishes soil nutrients, and shapes the landscape to sustain food sources and cultural sites. This is a delicate dance with fire as a partner, not an enemy. Some seasonal names describe weather and environmental changes. The Rembranga call a particular season Walcharn Miri, marked by wet conditions and inland travel restrictions caused by floods and lush vegetation growth. The Macassar fleets, migrating fishermen, recognized patterns in sea and wind, with their arrival timed for favorable northwest gales. Traditionally, Indigenous Australians relied on these calendars to time their hunting, gathering, and spiritual activities. Their intimate knowledge of nature meant they had complex calendars far removed from arbitrary months and seasons. The annual burning and ecological management helped prevent catastrophic bushfires that we see today. But the calendars are shifting now. Climate change is disrupting the cues, the flowering times, the animal behaviors, the weather patterns. Traditional knowledge keepers warn that seasons are not as they used to be. The disruption threatens ecosystems and cultural continuity. Efforts are ongoing to preserve this knowledge, to adapt, and to educate younger generations. These fire calendars represent tens of thousands of years of environmental observation. They are living records passed down through stories, ceremonies, and hands-on practice. Complexity, precision, intimate connection. The Aboriginal people weren't just surviving a harsh landscape, they were cultivating it, tending it, shaping it to their needs and beliefs. And in doing so, they created some of the oldest continuous environmental records on Earth. I walked through the smoldering remains of a carefully controlled burn, the smell of charred eucalyptus sharp in the air. This was renewal, not destruction. Thousands of years of knowledge living in practice. And as I breathed in, I thought about all the ways humans have observed climate, from bark and bone to ink and stone, from memory to modern machines. The story continues in the mountains of Europe, where villagers kept records of glaciers advancing and retreating, where fields disappeared beneath ice and reappeared centuries later. Their journals tell the story of a changing climate written in ice and water. The journey continues. Stay with me. In a village at the foot of the Alps, I found parish records dating back to the 15th century. They describe the glaciers. When they advanced, when they retreated, when they crushed homes, when they freed pastures. These records have been used by glaciologists to track the Little Ice Age in Europe. The villagers were not scientists. They were farmers, priests, and shepherds, but they documented what they saw, and what they saw was the climate shifting. Glaciers creeping forward, year by year, swallowing fields and villages. Then, suddenly, retreating. The records are so detailed that scientists can match specific years of advance to volcanic eruptions and solar minimums. One entry from 1645 described a glacier that had consumed an entire valley. When I visited that valley, I found the remains of old stone walls freed from the ice only in the last century. The glacier had retreated, but the record remained, and it tells us something critical. Climate has always changed, but the speed of change, that's what matters. And right now, the speed is unlike anything in these records. The Europeans living in Alpine communities relied on their environment for survival. Croplands nestled in valley floors, pasture lands for livestock, water from mountain streams. When glaciers advanced, they could destroy all this. When glaciers retreated, new land opened up for farming. Villagers kept meticulous records in church books. They documented harvest times, weather anomalies, and glacial changes. They witnessed glaciers overriding homes and farms, carving new paths, and retreating to reveal ancient soils. These records form a critical window into climate history. One striking example is the Great Glacier Advance in the late 16th and early 17th centuries, part of the broader Little Ice Age cooling. Historically significant glaciers, like the Morteratsch and Mont Mayan in the Swiss Alps, reached their maximum lengths in this period. Diaries recorded hunger and crop failures coinciding with these cold decades. The Glacier Chronicle entries sometimes mention dangers faced, the sound of ice cracking, floods from glacial lakes suddenly bursting, the loss of grazing lands. But they also describe hope, as glaciers retreated and new flocks were pastured. Modern scientists have digitized these records alongside geological data, mapping moraines, dating buried trees, and analyzing sediment layers. They synchronize human observation with natural archives. The glacier front positions recorded in parish documents match modern measurements from aerial surveys and satellites. These long-term glacier records have uncovered links to larger climate drivers, volcanic eruptions that ejected dust into the atmosphere, reducing solar radiation and cooling summers. Solar activity cycles influencing temperatures over decades. Periods of drought correlated with glacier advances during cooler, drier times. By the 19th century, glaciers began to retreat significantly, a warming trend that accelerated in the 20th century. Villagers who had once feared advancing ice now saw fertile lands reclaim valley floors. But even today, our climate is changing rapidly. Glaciers are shrinking at unprecedented rates. The Swiss Alpine glacier stories remind us that nature is powerful and patient. It moves slowly, but once in motion, change can reshape landscapes and lives. I stood in that Alpine valley, framed by towering peaks and the remnants of an ancient glacier. The air was crisp and cold, a stark contrast to the warming world below. The stones beneath my feet told a quiet story of time, endurance, and transformation. And just beyond these mountains, where glaciers give way to ancient forests, trees have been recording their own tales of climate, rings that count the years and seasons when the Earth was changing. The journey of discovery continues there. Next, we follow those silent witnesses, the ancient bristlecone pines of California, trees that hold the deepest memories of Earth's climatic dance. Stay with me. In Seoul, I was granted access to the Joseon Wangjo Silic, the royal chronicles of Korea's Joseon Dynasty. Within these records are daily weather observations spanning over 500 years. Every day, without interruption, court officials recorded the weather. Rain, snow, wind, temperature. It is one of the longest continuous weather records in existence, and it's astonishingly detailed. Meteorologists have used these diaries to study monsoon patterns, droughts, and temperature shifts in East Asia going back to the 14th century. I read one entry from the year 1783. It described a summer without warmth, strange fogs, and crop failures. When I looked up that year, I found the cause. The eruption of Laki in Iceland had sent ash around the world, cooling the planet. The Joseon scribes had documented the effects in Korea. They did not know the cause, but they recorded the symptoms with scientific rigor, and now their diaries are teaching us how global climate events ripple across continents. But here's the part that unsettles me. They recorded the weather every day, every single day. What were they preparing for? What did they think was coming? The Joseon Dynasty ruled Korea from 1392 to 1910. Its era spanned vast political shifts, wars, and cultural changes. But throughout, the Royal Secretariat maintained meticulous weather records. These diaries, such as Sungjangwon Ilgi and Il Sungnok, recorded precipitation data with precise timestamps, even noting hours of rainfall. This dedication to detail is unmatched for the time. Korea was among the earliest regions in the world to conduct quantitative rainfall observations, long before modern meteorological instruments existed. And this continuity gives scientists invaluable climate data, especially for periods like the Maunder Minimum, a time of extremely low solar activity and notable global cooling from around 1645 to 1715. During the Maunder Minimum, records show prolonged droughts, cold spells, and climate instability in Korea. The royal diaries mirror these conditions with entries on frozen rivers, failed harvests, severe winters, and unusual weather events. They also reveal the societal impacts, calls for grain relief, movements of people, and shifts in governance. Interestingly, researchers studying these records have linked their detailed rainfall observations to solar cycles. During years of low sunspot activity, rainfall decreased, leading to drought. This correlation reveals how solar variability influenced East Asian climate and, by extension, Korean society. The diaries also detail extreme weather events, floods destroying villages, locust swarms connected to dry spells, and severe frosts hitting crops during unexpected months. Such observations were critical for a society deeply reliant on agriculture and vulnerable to nature's whims. The weather diaries were more than mere records. They were tools of governance. The court used them for agricultural planning, military campaigns, tax assessments, and disaster response. Understanding weather was essential for maintaining political stability and feeding the population. Despite the challenges, the royal scribes kept writing day after day, generation after generation. The diaries provide us today with a rare window into a climate distant yet deeply interconnected with our own. I closed the heavy leather-bound volume, feeling the weight of centuries in my hands. Within these pages lies a chronicle of resilience, a people responding to shifting skies with precise observation and quiet determination. But as I set aside the diaries, a new question rises. How did other cultures measure the extremes of climate at the very edge of their world, where written pages gave way to ice and endurance? How was weather recorded when survival meant understanding winter's deepest cold? To find the answer, we travel from palaces and scrolls to frozen waterways in distant Europe. In the heart of the Netherlands, the story of resilience continues. Not in ink, but in the memory of ice. Here, the freezing and thawing of canals holds the keys to centuries of winters, community, and change. In Amsterdam, I stood beside a frozen canal reading accounts from the 17th century. The Dutch had recorded every year the canals froze solid enough to skate on. These records have become a key data set for understanding the Little Ice Age in Europe. When the canals froze, winters were brutal. When they did not, the climate had warmed. It seems simple. But the consistency of these records, maintained by civic authorities and private citizens alike, has given climatologists a reliable indicator of temperature shifts over centuries. The canals are not just waterways, they are lifelines of the Netherlands, a country built below sea level and crisscrossed by dikes, locks, and channels. For centuries, canals were highways as much as rivers. In winter, when frozen, the canals became giant skating rinks, connecting towns and villages, turning the country into one vast winter festival. The oldest frieze records date back to the late 1600s, coinciding with the harsh winters of the Little Ice Age. One famous frieze was during the winter of 1683 to 1684, known as the Great Frost. The canals froze solid, the rivers iced over, and even the sea near the coast turned to ice. The Dutch froze in place. People skated for miles. Children played hockey on frozen canals. Markets shut down. The frost lasted for months. The records tell stories beyond just the freeze. They describe snowfall, frost patterns, and temperatures. Town minutes recorded the impact on transportation and trade. Hospices and the poor were documented as suffering during these freezes due to cold and scarcity. And yet, there was joy. The canals became festival grounds, temporary towns of ice houses, food stalls, musicians, and skaters sprung up, creating one of the most unique winter phenomena in the world. The Dutch tradition of canal skating inspired literature and culture. The tale of Hans Brinker, the boy who stuck his finger in a dike to stop a flood, is legendary. The Elfstedentocht, or 11 Cities Tour, is a 1,000-kilometer speed skating race that takes place only when the ice permits, usually about 15 times a century. It rallies tens of thousands of skaters who travel from city to city on frozen canals and lakes. The race encapsulates Dutch identity and endurance, linking past and present. But recent decades have seen fewer freezes. Climate change and urban pollution have warmed winters and reduced ice thickness. The canals no longer freeze consistently enough for the Elfstedentocht to occur regularly. The longest freeze drought was from 1962 to 1985, 23 years without the race. Public anticipation builds during cold spells. When the canals freeze, people flock to the ice, sometimes risking injury or worse. Hospital emergency rooms fill with fractures from falls. The Dutch government issues warnings to keep skaters safe, but the allure of skating on centuries-old waterways is irresistible. Scientific studies have used Dutch freeze records alongside other proxies to understand historical climate patterns. These data confirm the Little Ice Age was a period of prolonged cold, punctuated by harsh winters that could freeze large parts of the country. Then the warming trend of the 20th century brought milder winters, and the ice events became less frequent. Reading the freeze records, one senses the rhythm of a world tied to ice and cold. The canals froze not just water, but time itself, connecting generations through a shared experience of winter's grip. These freezes were markers of climate, community, and resilience. Standing on the edge of a frozen canal, imagining centuries of skaters before me, I thought of the fragile balance between nature and culture. The ice that once held this country together is now thinning, disappearing in the face of warming oceans and skies. And then I wondered about history's final weather record, not in ink or stone or memory, but in the Earth's pulse itself, tree rings, ice cores, and sediment beds. These natural archives carry whispers of forgotten climates and unfolding futures. Before we close this journey, one last reflection awaits. Because history never ends, and the past is never entirely lost. Stay with me for the final chapter. After exploring 15 unique and detailed ancient weather records, the journey leaves us with a profound sense of wonder and reflection. From the clay tablets of Babylon to the frozen canals of the Netherlands, human beings have sought to understand the skies above and the lands beneath their feet. They watched, they recorded, they adapted, and through their efforts across vastly different cultures and times, they created archives that now speak to us across millennia. These records reveal more than just temperature and rainfall. They show us the intimate connection between people and their environment, how climate shaped harvests, migrations, wars, and even the rise and fall of empires. They tell stories of resilience in the face of famine, hope amid the chill of strange winters, and faith pressed into service of survival. Perhaps most striking is how these ancient observers, without modern instruments, developed systems of understanding that challenge our assumptions about knowledge and science. Whether through observing the blooming of Sakura, carving measurement marks into stone, or passing down oral maps etched in memory, they captured the rhythms of nature with remarkable precision. But the shadow beneath these discoveries is clear. Despite centuries of watching and recording, civilizations could still be overwhelmed by climate's power. The Mongol conquests, the collapse of the Mayan cities, the decline of the Roman Empire, and the hardships chronicled in monastic diaries all speak to climate as a force that shapes human destiny in profound ways. This exploration reminds us that history does not whisper, it waits. It waits in layers of sediment, in tree rings curled by time, in parchment worn by hands long gone. It waits in frozen canals, in the cracks on ancient bones and stones. These are stories waiting for us to listen deeply. And now, standing in the present, armed with technologies unimaginable to those ancient chroniclers, we face our own climate crossroads. Their records offer clues, warnings, and deep humility. They tell us that climate change is not a new story, but our response to it may be. As this chapter closes, a question lingers. What will be recorded in the future's archives? How will those who follow us read the signals we leave behind? The journey continues beyond history into what we choose to do next. Thank you for walking these paths with me, the Explorer of Erased Epochs. The past has opened its pages, but the story is far from over. Keep watching, keep wondering. There is much more to discover.